All right, now it's being recorded. I'm not sharing this yet. Any questions before we get started? So the homework was posted rather late last night, so I apologize if you haven't got a chance to work on it earlier. It's like a 20, I think it was like 27 or 28 questions, but a lot of them are graphing. You don't actually, well, I don't think you actually have to graph them because they give you the choices to choose. So that hopefully will take less time than the normal homework set. Let me know if you work on it and then you feel like you just spent too much time on it. Let me know. All right. Before I get started, I want to show you this website. I'm sure some of you know it already. It's called Asymptotes.com. It's a very convenient website. I think it's also easy to learn how to use it if you never use it. It just basically is an online graphing tool that it's better than the one on your graphing calculator. It's called Asymptotes.com. I'm sure some of you know it already. I just want to use it to show you a couple examples. So new share. Let's see. So when you first go to this website, it looks like this. And let me make this smaller. Get this out of the way. So basically on the left side, you put in the functions, and you can actually use variables like an A and a B as variables. And after you type them, they're going to give you the option to add those variables as sliders. So that's what I did. And on the right side, those are the settings, and then you can change, get rid of the gray line, the minor gray line. It's up to you. So you can get rid of those and then change the X, Y intervals that displayed, and then change the steps, the units on each axis. So what I want to show you is I want to take A to be +1 with this power function y equals AB to the X. And let's see, leave it there. And then I want to show you what happens when we change the B value. For example, I'm going to begin the B with B is between, let's see, 0 and 1. B is just from 0 to 1, and then the steps, I'm going to make it to be 0.1, for example. I want to show you what happens. So right now I have B is 1. And if I change the B value from 0, so B 0, that's just a line, y equals 0, because 0 to the X equals 0, 0 times A is 0, right? And then if I increase a B from 0, as you can see, it gives me this like exponential decay graph. As B getting close to 1, the graph is actually getting flatter. It's not as steep it is near the y-axis. So play it again. So that's B equals 0.1, and then 0.2, 0.5, 0.8. As you can see, become flat. Now it goes backwards from 1 to 0. So as you can see, I just want to show you what happened there. For B is from 0 to 1. Now, if I change the interval from 1 to, for example, 10. So now B is greater than 1. And I'm going to make the steps to be, doesn't matter, 0.1, whatever. And what happened is, as I move the slide B, so now it's the exponential growth, because as X increases, the Y increases. So the B value will determine how steep the growth is. As B increases from 10, from 1 towards 10, and the shape of the exponential growth part is just going to get steeper and steeper, and it's kind of approaching the Y-axis in some sense. So that's what the B value. As B gets bigger, the growth is steeper. The A, it doesn't change anything because I keep A to be 1. Now, what if I leave B the same? So let's say B equals 2.2. I have this exponential growth because B is more than 1. Now A is 1 now. What if I increase 1? Now it looks like the graph is sort of like being rolling upwards. It's actually being shifted upwards. It's just difficult to tell. So the whole graph, sorry, it's not being shifted. It's being like stretched upwards. So that's A is a vertical stretch. So it's all the values on the curve is being multiplied by this factor A. And the A is smaller, so it's kind of the vertical compression. So now A is 0.7, and I'm going to getting smaller and smaller. So as A gets smaller, there's a vertical compression, so the graph is kind of squeezed towards the x-axis. As A become negative, we all of a sudden flip the graph over the x-axis. It's a vertical reflection. And in that part, as A changes, it's just kind of doing the same thing again. So stretch vertically, but in the negative y direction. I just want to show you this. So that's the graph of y equals AB to the x. Okay. And the next thing I want to show you is the graph of log base B. So I'm going to change the B value from 0 to 10. Remember, B has to be positive, right? But B cannot equal 1. So as you can see right now, B equals 1, we don't see anything. But what if B increases from 0? So B equals 0, there's nothing. As B increases from 0 to, oh, I didn't show the graph. So here you go. So B equals 0, there's nothing. B equals 1, there's nothing. Right? But if for B is from 0 to 1, as B increases, as you can see, we still have this, I guess, sort of decreasing function in the first and the fourth quadrant, but as B increases, it becomes more like a straight line towards the y-axis. So that's B equals 0.1, 0.4, 6, 0.7, 0.8, 0. So it becomes more straight line-like as the B value approaches to 1. Now, after B becomes 1, so we get this sort of flipped graph. So now it's increasing. By the way, this point it touches, that's a 1 to 0, it doesn't move. So if I increase the B, it becomes flat and flatter towards the x-axis. Again, this point stays, the vertical asymptote stays, doesn't move. It's just the graph itself, it's become more flatter as the base increases. All right, so but the overall shape is the same. For B more than 1, you kind of always get this like increasing on the function that slows down over time, but it's still increasing all the time. And for B that's between 0 and 1, you always have this like a decreasing graph. Again, that graph has a vertical asymptote y equals 0, and this x-intercept 1, 0. I mean, vertical asymptote x equals 0, and this x-intercept. I want to show you this. You can play with it. You can type any function you want to graph, like absolute value function, anything. I found it pretty handy to use. It's a good website to use if you want a graph that you can use it for your calculus class in the future or for this class. Yeah. Questions? All right. If you don't have a questions, I think I'm going to get started with today's lecture. So today we're going to graph log functions. We already know, earlier we saw what the logs look like. So log f of x equals the log base b of x. So the graph either going to be a decreasing, goes through this point 1, 0 with a vertical asymptote, or it's going to be increasing, goes through this same point 1, 0 with the vertical asymptote. So this left side of B is between 1 and 0. The right side is B is more than 1. Right. So that's a graph. And so obviously that's a vertical asymptote, and that will determine what the domain is, because the domain always starts from the vertical asymptote. All right. So given the log function, so given f of x equals log base b of x, how do we find the vertical asymptote and how do we find the domain? So to find vertical asymptote, what we're going to do is we're just going to take this part inside the log, the x there, we're going to set it equal to 0. So this part equals 0. So that will give us a vertical asymptote. Even though that part cannot be 0 when we talk about the graph of logs, the function log, but if we just want to find that vertical line that the graph approaches to, it's perfectly okay to have it equal to 0. And to find domain of this log function, remember that we said it before, for log functions, whatever in the parentheses inside the log, that has to be positive. So that means, again, this part has to be positive. So x, the part in the parentheses, the x has to be positive. Now, if we have like a 2x minus 1 inside the parentheses, then 2x minus 1 has to be positive. So whatever in the parentheses has to be positive. So that's how we're going to find the domain and the vertical asymptote. But they're connected. One is equal to 0, one is greater than 0. So here's the example. Find vertical asymptote and domain of the function f of x equals log of 2x plus 5 minus 10. Well, there's the extra part, minus 10, but that's subtracting 10 from the y, the log part, so it doesn't really affect, it just means to shift it down by 10, but it doesn't affect the x values of the vertical asymptote. So to find the vertical asymptote, what we're going to do is we're just going to take this part inside the log, we're going to set it equal to 0. So 2x plus 5 equals 0. So this is where we're going to look for the vertical asymptote. And then move the 5 to the right, become negative 5. So you get 2x equals negative 5 divided by 2x equals negative 5 half. So it's a vertical line. Remember, vertical asymptote is a vertical dotted line. So it always goes through one specific x value. That's why we have x equals. It's not just the x value, it's a vertical line. That's a vertical asymptote. Now, what if I want to find the domain? Now, be careful. Domain is not just simply changing the equal sign to greater sign. In this case, it is, but it's not always the case. If we have a minus 2 times x plus 5, it will be different. So be careful there. So the domain will be, take again the shaded part, the 2x plus 5, and we want it to be greater than 0. We need to make sure whatever it goes into the log is positive. Solve for x. So minus 5 minus 5, 2x greater than negative 5, x greater than negative 5 half. So that's the domain. Put it in the interval notation. So that will be from negative 5 half to the right, but does not including negative 5 half. So that's a domain. This question did not ask you to find the range, but for all logarithmic functions, the range is always going to be from negative infinity to infinity, because the y values can go all the way up to infinity and a negative infinity. So range is simply negative infinity to infinity. Just like the domain for exponential functions, it could be any x, so from negative infinity to infinity. All right, any questions about this example, finding vertical asymptote and the domain? Okay, now I want to give you another example. We're going to do the same thing. We're going to find the domain and find the vertical asymptote and the domain of the function g of x equals 3 minus natural log 1 minus x. So here we talk about natural log. It's just treated as a log base e. It's just a normal log. If we want to find the vertical asymptote, we have to take this part inside the log, set it equal to 0. So we get vertical asymptote is going to be 1 minus x, set it equal to 0. We can move the 1 to the other side, or we can just plus x on both sides. So we get 1 equals x, or x equals 1. That is the vertical asymptote. And then to find the domain, again, it's not just going to be x greater than 1. It's not that simple. So what we have to do is we take the same part inside the log, 1 minus x. We're going to set it greater than 0 because we want that to be positive. And from here, again, we can either move the 1 to the other side or add x, whichever you prefer. Normally, the teacher probably like, oh, subtract 1, multiply by negative. What's the sign of the inequality? But a quick way is just adding x to both sides. So I got 1 greater than x. Another way to read this is x less than 1. So that equivalent, or in the interval notation, is going to be from negative infinity to 1. So that's a domain. As you can see, it's not simply just changing the equal sign to positive to greater than, is actually less than 1 in this case. So be careful with the domain and the vertical asymptote. They are associated with the same value, but we have to be careful which side of the vertical asymptote is the domain. Okay, let's see. Any questions about those examples? All right. The next thing I want to do is let's graph the parent function. So graph the parent log function, which is f of x equals log base 5 of x. So we want to graph it. So if we just want to graph it, what do we do? Well, the first thing we're going to do is we need to know the vertical asymptote, because that's going to tell us how the graph is going to approach that vertical line and where the graph stops. So find vertical asymptote. So that's going to be taking this part inside the log, which is just the x. It has to equal to 0. So set x equals 0. There's no need to solve for anything. So x equals 0. The second step for this parent function, log base 5 of x, if you remember earlier when I was showing you this log base b, doesn't matter what the base is, they always have this point 1, 0 on it. So, and doesn't matter, b could be like, a million, any number. The x-intercept does not change 1, 0. So that's my second point. That's the first point I'm going to use, but then for the second step, so graph the point 1, 0, because that point is definitely going to be on this function. And the step 3, we're going to graph another point. This is what I want to show you using the Desmos. So let's see, b equals, I'm going to change b to be, hold on, let me change the scale to the x steps to be 1. The y steps also 1. Okay. And I want to change it, just pick some b values. So let's see, b is, let's see, b equals 2. So as you can see, b equals 2. The graph goes through this 1, 0 point, but it also goes through this 2, 1 point. Right there, somehow I could have put a point there. Oh, there you go, 2, 1. So this point 2, 1 is there. Now, if I change it b to be 3, as you can see, b equals 3. Now that point 2, 1 actually moved to 3, 1. And if I change it b to be 4, and that's 3, 9, so 4. Now that point, instead of having it at 2, 1 or 3, 1, now it's located at 4, 1. right there. And if I increase b to 5, and at that point, the nice point is actually at 5, 1 now. I couldn't right there. Difficult to get that point, but as you can see, it's right there. And if I increase b to 6, the nice point, in addition to 1, 0, it's going to be 6, 1. So the nice point we have is always going to be 1, 0 and a b comma 1. Let's say b equals 7. So now this 7, 1 is the nice point. B equals 8. 8, 1 is a nice point. And b equals 9. 9, 1 is a good point. And b equals 10. It's kind of difficult to tell, but you can see that 10, 1 is a nice point. So I just want to show you that the two nice points on this graph. One is 1, 0. The next one is the b comma 1. So for this specific example, when we want to graph log base 5 of x, this nice point is going to be 5, 1. So that's the 2 points and the vertical asymptote, and then we can graph the function. So that's going to be 1 here, 2, 3, 4, 5, 6. And then we have a vertical asymptote at x equals 0. This point 1, 0 is a good point, and the 5, 1 is a good point. So we have 2 points and a vertical asymptote. We draw a nice curve through this x-intercept. And then we get this graph. So this is, it doesn't cross the x-axis, it's just approaching it. So this is the log base 5 of x. Any questions about graphing this? Again, you don't need 3 points here. Obviously, if we have more points, nice, right? But if we only have 2 points and a vertical asymptote, that's already giving us a nice graph. To be honest, I don't think I'm going to ask you to graph this by hand, and I don't think any professor or teacher is going to ask you to graph it by hand in the future. But you might end up with someone as you actually do the work. But let's graph log functions by using transformations. So graph log functions as transformations of the parent function. Just like any function we talked about before, you always have a basic, the parent function, and then you have those things, those variables that will do different things to the function. But they're actually all the same, it's just different way because of the parent function is different. For example, so given parent function f of x equals log base b of x, if we transform this f of x and we end up with g of x equals a log base b x minus h plus k, it's always the same. So what we have changed is this x, we change it to x minus h. The log base b of x, the log part, is sort of like the y. So we took that, we multiplied by a, then we added k. So what does each of these variables do to the function f of x? Well, if we minus the h from x, so that means we're going to shift it to the right, or it could be left, depends on the value of h. Now, if we add a number to the log, so that's why we plus a k at the very end, so we add it to the log, which means to the parent function f of x. So that means we're going to move it up or down, just like before. And the a times log, so that's kind of like the vertical stretch, vertical compression. If a is negative, it could be a vertical reflection, a flip over the x-axis. So all those values are the same, have the same meaning, just like we have done with quadratics, with absolute value function, with exponential function. You just have to know where we associate those constants, right? Is it in front of the log? Is it inside the log? Or is it added or subtracted at the end of the log? If it's, is it multiplied or is it added? So that's going to tell a difference. Okay, so let's graph a few functions. Let's see, before I do that, one quick comment about horizontal reflection. So if you remember, if we have a horizontal reflection, we're going to take the positive x and make it negative, right? So if we given, so this is the case, so this is part A, for example, this is part B. Suppose we given that f of x equals log base b of x again. And I'm going to call this h of x, which is going to be log base b of negative x. Maybe I'm going to put a negative in front of it too. So that's two negatives. Now the negative in front of it, because we basically take log base b of x, the parent function, we multiply everything by negative. So that means we can actually multiply the y part by negative. So this is the vertical reflection over x-axis. But if we only multiply x by negative, but leave the y the same, so if we multiply x by a negative, and we really reflect horizontally. Hopefully by now you remember those transformations. So here's the example. What we're going to do is we're going to sketch a graph of f of x equals 5 log x minus 2 plus 4. We're going to graph it not just using this function, but using transformations. Using transformations on f of x equals log of x. So now it's the log of x, means log base 10 of x. So the graph is going to have a vertical asymptote. I'm just going to graph the function f of x. I should use a different letter so that it's not confusing. Let's say call this y. Y equals log of x. So vertical asymptote at x equals 0. That's for all parent function log base b of x. And it goes through this point, 1, 0. And since we have log base 10 of x, so it's going to go through 10, 1. But I'm just going to quickly graph like this. I don't really care about the last point. The 10, 1. The overall shape is like this. And what happened to this function first? Well, let's look at the given formula of f of x. So we have 5 times log x minus 2 plus 4. So 5 means it's a vertical stretch by 5. And x minus 2 means we move it to the right 2. Plus 4 means we move it up 4 when we add 4 to the log. So it doesn't matter which one you want to begin to draw. Let's see, suppose we want to work on the vertical changes first, right? The vertical changes multiply by 5 and then shift it up 4. I need to move this down a little bit. So if I multiply all points on this, the y coordinates of all those points, we multiply by 5. We just stretch it vertically by 5. The 0, 1 stays, the 1, 0 stays. The vertical asymptote, even if we stretch it vertically, it doesn't go anywhere. So it stays. And this 10, 1 is going to be 10, 5. 1, 2, 3, 4, 5. And all points between those 2 points, the 1, 0 and the 10.5 will be scaled appropriately. Now, what about negative? Well, let's just say we have this point that has a negative y value. Well, that's also going to be stretched by a factor of 5. That's going to be more negative. So this point is just going to be 1, 2, 3, 4, 5. I think my graph is a bit tall now. So anyway, so we get this like a really skinny tall graph. So this is a vertical stretch by 5. 5 times the log of x. And after that, we have to shift it up 4 units. So if we shift it up, so the 1, 0 will become 1, 4. So 1, 2, 3, 4. So that's 4 units up. And then this, I think that's 10.5. So that point 10.5 is going to be 10.9. So I'm going to run out of space, 6, 7, 8, 9. I'm just going to estimate somewhere there. The vertical asymptote, even if we shift it up, is still there, so it doesn't go anywhere. And the points below, it's going to move it up 5.5 units. So we end up with this graph going like this. Oops. So that's a graph, 5 log of x plus 4. So that's shifting up 4. The last thing we have to do is move it right 2. So when we move it right 2, I'm just going to do a bad job here. I'm going to not even care about the scale. So that's 1, 2, 3. So this point, if we move it right 2, we get 1, 2. The vertical asymptote, if we move it right 2, we go from x equals 0 to x equals 2. So that's my new vertical asymptote. This is my new point that originally was on the x-axis, the x-intercept. And this point, when we move it right to 1, 2, so now we get this point, that point, and the vertical asymptote. So if I draw it, I get this graph. So this blue curve is going to be 5 log x minus 2 plus 4. Any questions? I promise you, if you had a graph paper, it would be a whole different graph. It will look a lot nicer than what I did. So now we graph it. We can talk about a few things. We can say, okay, what is the domain? What is the vertical asymptote? What is the range? So with the graph, we can just identify the vertical asymptote is at x equals 2. Let's say we don't have a graph, we can still find out the vertical asymptote, which is using this part. X minus 2 must equal to 0. X equals 2. Same thing we get on the graph. How about the domain? Again, we can look at the graph. It's going to be everything to the right side of this vertical asymptote. So going from 2 to infinity. Or we can just look at the part in the log. So x minus 2 must be positive, x greater than 2. Another way to write it, that's from interval notation will be from 2 to infinity. Now, what about the range? Well, the range, again, this is a logarithmic function. It's just the transformations of log. So that's still going to be from negative infinity to infinity. So the both ends of the graph goes infinitely in both directions. So that's a graph. Any questions? Okay. All right. So that's finding the vertical asymptote, domain, and range. You can look at the graph, or you can just use the formula given, the function. Now we're going to graph another. Now I feel like I'm probably moving a little bit too fast. I know it's difficult if you try to copy down the graphs and take notes when I'm talking. So I'm going to pause for a minute. By the way, I don't think today's class is going to take very long. We're doing pretty good with the material. There's a few things I have to talk about. But after that, I think we should be able to finish early again.
Oh, just for future reference, I was wondering, do like future exams, will they cover what we went over on like our last exam?
No, good point. So the way I'm imagining the quizzes and the exam is that, so the quizzes obviously just going to cover, you know, whatever we talk about between the quizzes, right? And exam is not accumulative. It's only going to cover whatever we did not cover from the last one.
All right, thanks.
Yeah, to be honest, I personally don't see any point of giving a cumulative exam for this class, or like covering whatever we covered in the past. It's just not necessary, because I want to know how much you understand as we progress. Not, I mean, obviously it's nice to have the exam talk about, you know, to cover everything, but it's just not necessary for this one, like 2 months long class. Good point. But I do want to point out though, there might be concepts that we studied on before we took that exam. We might use some of the concepts on this new exam. For example, it might be, oh, this is a compounded interest problem. Like instead of asking you to set up the formula, the function as the main point, but the main point of the question might be, okay, how many years does it take to reach this amount? So you do have to know the compounded interest formula to get it correct, even though that's not the main point of the question. Or if it says, oh, here's this exponential function, y equals 2 times 1/2 to the x. What is the, let's see, what is the x value when y equals 5? Something like that. Yeah, it wouldn't be specifically based on the concepts in the past. It's more like just use it as a foundation. Good. All right, so that's this graph. The next graph I want to quickly graph is, let's say g of x equals negative log of negative x. So for this graph, well, actually, let me change it to natural log, because it doesn't really change anything. It's just the same graph, basically. The scale might be a little bit different if we try to be accurate, but here we just draw a quick sketch. So the first thing we do, we have to figure out what kind of transformations happen. So this negative is going to be flipped over x-axis. This negative inside the log is going to flip over y-axis. It's a horizontal reflection. The other one is a vertical reflection. I just want to use this to kind of draw the parent function for natural log of x. So we're going to begin with natural log of x. Natural log of x has just like a log base 10 or log base 2, it has a vertical asymptote at x equals 0. And then it goes through this point 1, 0. Since natural log is log base e, so it's going to go through another point called e1, and e is about 0, is about 2.7. So that's 2, that's 3, 2.7 is about here. So 2.71. So this is e, 1. And if we graph it, it looks like this. So this is the natural log of x. And the first thing we can do is we can reflect this over x-axis. If we reflect this over x-axis, the point on the x-axis stays the point. This is a E1 will become E-1, just literally reflecting over the x-axis. So we kind of get this graph. Same vertical asymptote. And the next thing we're going to do is we're going to reflect this new graph. So this is the negative natural log of x. We need to reflect it over the y-axis. So this e negative 1 now it becomes negative e. So let's see, -1, -2, -3, negative e is here. So negative e, -1 will become this point. And we still have this vertical asymptote when we reflect the function over y-axis, so it doesn't change. And this 1, 0 will become -1, 0. And we end up with this graph. So this is a negative natural log of negative x. Okay. All right, any questions? Okay, so if you don't have questions, I'm going to move on to the next section. I have a question. I'm imagining that we're probably going to finish in about maybe another 30 to 40 minutes. Do you want a break before that, or do you just want to kind of go through today's class and finish early? Well, let's see, anyone wants to take a break before we finish the class, like take a break in the middle of the lecture. If you want that option, let me know. If no one wants that option, I'm just going to keep going until I finish. All right, I'm not seeing any objections, so I'm going to keep going. Like I said, we should be done in about 30 to 40 minutes. We don't have a lot of material to talk about in this. Well, it's a lot of graphing, but the graphs are not really that complicated with logs, as long as you think about transformations. All right, so the next thing I'm going to talk about is log properties. This is section 4.5. We already talked about properties last time. So if you haven't got them memorized, you do need to memorize them. This is probably the important properties that you need to memorize in order to do well in the future when you see logs and exponentials. So I'm not going to rewrite them. So just remember, go back to the previous class. Let's see, so we had quite a bit log properties at the end. So all of those are important, including the very last one when we change the base by converting into a division of two logs. All right, so just make sure you review those and have them memorized. So let's begin with the example. To find, so here's the example, we're gonna find log base 9 of 1/27. We want to know what that is. I don't know what that is. So what I'm going to do is I'm going to convert this into exponential function at some point as exponential equation. But what I'm going to do is I'm going to call this x. So x equals this log base 9 of 1/27. And then I'm going to convert it to exponential. So if you remember, when we convert to the exponential, the base doesn't change. So 9 is a base in the log. So the base of the exponential is still 9. But now we need the exponent and we need the other side of the equation. And all we do is we're going to switch those two parts. One is next to the base in the log. The other one is away from the log on the other side of the equation. So when I switch, so the x will go with the 9, 1/27 will go to the other side. So this problem is a little bit challenging, but I think we can manage it. So let's think, okay, 9 to what power give me 1/27? It's not easy. So we have to do is we have to convert both parts to the same base. I know that 1/27 is 27 to the -1, so 27 to the negative first power. That's 1/27. That doesn't help. The base is 9 on the left, the base is 27 on the right. Let's keep going. So I know that 27 is 3 cubed. So I get 3 cubed raised to the -1. That's the right-hand side. And that's equal to 3 to the -3. So base 3 with a -3 in the exponent. Okay, that's still not helpful because the left side still have a base 9, the right side has a base 3. Well, let's rewrite 9. So 9, if we rewrite it, that's a 3 squared raised to the power of x. And then we can rewrite this as 3 to the 2x. 2x is the exponent. So now we convert both sides to the same base 3. We can actually say, okay, since this is the equation, the base are the same, therefore the exponents must be the same. So we get 2x equals -3. And we can solve for x. So x equals -3/2. So that's the value for log base 9 of 1/27. That's equal to -3/2. Any questions? I think this is a good example because it's not straightforward. It's not like, oh, log base 9 equals this. By writing it, then I know what the answer is. So you have to do a little bit rewriting, a little bit conversion there. But eventually we can find the x. So that's one example of the review. Let me know if you have any questions.
I have one question.
Okay, go ahead, please.
Let me turn my camera back on. How does the 2x minus is equal to -3 come in? Like, where do you, oh, I think I see what you did.
It coming from here. So what happened is that eventually left side and the right side both have the base 3, right? So the left side becomes 3 to the 2x, the right side becomes 3 to the -3. Now, since they have the same base on both sides, that means it's equal, and that means the exponents must be the same as well.
Okay, that makes sense. Thank you.
Yep, good point. All right, any other questions on this example? But again, if you are asked to, evaluate log of some number, and then you don't know what to do, just write it equal to x and then rewrite the entire expression to be exponential. It's a lot easier to work with exponential expressions because we are more familiar with it. Okay, so that's one example. The next example I have is, let's see. So we're going to expand log base 2 of 5x to the 4th x minus 1 with the denominator 3x plus 4 times 2 minus x. Now you probably think, okay, there's a lot of terms here. Don't panic. All we do is we're just going to use the rules we talk about, the product in the log or the quotient in the log to rewrite them, or maybe the exponent. So we're going to use those to rewrite those terms. So the first thing I'm going to do, what I see is I see a division. So I'm going to use the quotient rule with logs. So I get log base 2. So a quotient rule says log of a quotient equals the difference of two logs. So log base 2 of the numerator 5x to the 4th x minus 1 minus log base 2 of the denominator 3x plus 4 times 2 minus x. So that's the first thing to do, to separate the quotient. And now looking at each, I see products in each log. The left side I have, well, it depends on how you look at it. There's multiple items we multiply. We have 5 times x to the 4th power times x minus 1. And the second log, we have 3x plus 4 times 2 minus x. So we can use the product property to separate those logs. So that becomes log base 2 of 5 plus log base 2 of x to the 4th power plus log base 2 of x minus 1. So that the 3 terms coming from the first log. And then I'm going to subtract, because I have a product, so I'm going to add a bracket so that I don't make mistakes. So I'm going to subtract the second log becomes log base 2 of 3x plus 4 plus log base 2 of 2 minus x. So we use the quotient rule first, and then we use the product rule to rewrite the logs of products. And we're pretty good. And if we look at each one of them, the first one, we already simplified to the most simple form. We cannot do anything about it. The second one, we have an exponent. Maybe we can bring the exponent to the front. That's something we can do, so that 4 could go to the front. And the third one, log base 2 of x minus 1, be careful, nothing we can do here. So this part, even though we have a subtraction in the log, we cannot apply any rules to rewrite it. So cannot rewrite. We just have to leave it. We can only rewrite if we have a product, a quotient, or if we have an exponent inside the log. Again, the next term in the bracket with 3x plus 4, we cannot rewrite. And the same thing with the log base 2 of 2 minus x, we cannot rewrite. So those with addition and subtraction, we just have to leave it. We cannot do anything about them. But we can distribute the negative in front of it if we want. So now, if we rewrite this, we get log base 2 of 5 plus a 4 comes to the front, so 4 log base 2 of x plus log base 2 of x minus 1 minus log base 2 of 3x plus 4, distributing the negative not into the log, but with the log, like in front of the log. And then also in front of this log, so minus log base 2 of 2 minus x. So that's the fully expanded version. Any questions? So remember, you can only expand it if you have a quotient, a product, or a exponent, not with additional subtraction. Okay, so the next one I have is we're going to again expand natural log of square root x plus 1 2x plus 1 cubed divided by x squared minus 9. And we want to expand fully. So by looking at it, what I see again is a quotient jumping up, right? And then in the quotient, the numerator has a square root, the denominator is x squared minus 9. So I'm going to use the quotient rule first. So that's going to be a subtraction of 2 natural logs. So natural log of square root x plus 1 times 2x plus 1 cubed minus natural log of x squared minus 9. Okay, you probably think, okay, what do? We have a square root, and in the root we have a product. What can we do? Well, there's a couple of things we could do. We can rewrite the square root as an exponent. And then we can bring the exponent in front, make it easy. So that will become natural log. This step is just rewriting. Natural log of x plus 1 times 2x plus 1 cubed. Together, they have this square root. So together, they have 1/2 as the exponent. Which we can distribute into the exponents, or we can put it outside. I personally prefer to put this 1/2 outside in the next step, become a coefficient. Or you probably wonder, okay, what about the second log, natural log? It's natural log of x squared minus 9. Is there anything we can do? It is a subtraction, that's true. If we see it as a subtraction, we can't do anything about it. But we can actually factor that into a product. So this becomes natural log of x plus 3, x minus 3. With the subtraction, we cannot do anything, but now it's a product, we can use the properties of product. Okay, so the next thing I'm going to do is I'm going to bring the 1/2 to the front. So I get 1/2 times natural log x plus 1, 2x plus 1 cubed, minus, I'm going to use the product property. So that's going to be natural log, I'm going to put in a bracket, natural log x plus 3 plus natural log x minus 3. And we just have to keep going until everything is fully expanded and we cannot do anything about it. And it looks like the one on the left, we still have a product in the log. So that becomes a 1/2 times, become a sum. So natural log of x plus 1 plus natural log of 2x plus 1 cubed. And the two natural logs from the second part, it's just the way it is. We cannot do anything because this addition and the subtraction, they're not multiplication anymore. So leave them. And that becomes minus natural log x plus 3 minus natural log x minus 3. Well, almost done. We have 2 more lines to write for this part. And looking at all the terms, the first term, the first natural log, we have to leave it. But the second natural log, we can bring 3 to the front of the second natural log, not all the way to the front, just to the natural log that contains the cube term. So we get 1/2 bracket natural log x plus 1 plus 3 natural log 2x plus 1 minus, close the bracket, minus natural log x plus 3 minus natural log x minus 3. And the very last step is distribute the 1/2 into the first bracket. So that's a 1/2 natural log x plus 1. I distribute there, so plus 3/2 natural log 2x plus 1. And then we have minus natural log x plus 3 minus natural log x minus 3. So that's a fully expanded form. Now, I know that you probably wonder that we have a product 2 times x in the second log. That's a product. Can we rewrite it? Well, the answer is no, because we have addition. So it's not 2 times everything in the natural log, right? It's only 2 times a part of it. So it's not really a product in the log. It's actually addition in the log. So we cannot rewrite that log, just have to leave it. All right, let me know if you have any questions. I know I went through a bit too fast with this 2 examples. Let me know if you have questions there. All right, the next thing we're going to do is, instead of expanding, we're going to take multiple logs, put them together as a single log to condense them. Again, we're going to use those properties with logs. So condense logs. Example is, the first one I have 3 parentheses, natural log of x plus natural log of 7 minus natural log of y. I want to take this, put into a single log expression. So the first thing I'm going to do, don't worry about the 3 outside, worry about whatever is inside the logs. So I have addition of logs, so I can turn that into a product inside the log. Then I have a subtraction, so that means it's going to be a division in the log. So that becomes 3. Let's worry about the first part. That's the natural log of x plus natural log of 7. So that's the natural log of x times 7, 7 times x in the log, minus natural log of y. And now we can combine the subtraction of logs, become a quotient inside the log. So that's a 3 times natural log 7x divided by y. Now, what about the 3? Well, that becomes an exponent when we want to put it inside the log. So that becomes the exponent there. So that becomes natural log of 7x over y cubed. Now, every part in that fraction is going to have this cube. So if we want to rewrite it, so that becomes natural log of 7 cubed x cubed y cubed. But to be honest, if you leave it like this, that's much better. There's no point of distributing the cube in this case. All right, any questions? We just like practice those properties backwards. Okay, one more example here. If you don't have any questions. So this second example is similar. We're going to condense the logs into a single log. So I have log of 5 plus 0.5 times log of x minus log of x minus 1 plus 3 log of x plus 5. So again, just looking at this, we have addition, subtraction, addition. And we have some logs by themselves, some logs have coefficients. If we want to combine all of them, what we have to do is we have to take the coefficients, bring it inside the log first, so that way all the logs don't have anything in front of it. So 0.5, we have to bring it into the log. The 3, we have to bring it into the log first. So that becomes log of 5 plus log of x raised to the 0.5 as an exponent. I don't like 0.5 being exponent. I'm going to put 1/2 there as an exponent. Minus log of x minus 1 plus log of x plus 5 cubed. And if you want, you can write x to the half as square root of x. But we can just leave it if we don't want to rewrite that part. So now I can actually combine the parts, the logs, because I have addition, subtraction, there's nothing in front of the logs. So those two, addition means it's going to be a product. And if we want to do all of them together, so the first 2 is a product, the first 3 is going to be a product, and then divided by a term because that's a subtraction. Every time we subtract, inside the log become a division. And then we add again, so that become a product. So if I'm being lazy, hopefully that's okay. Let me know if it's confusing to you. So I end up with log. Inside the log, I have, first of all, the product, which is 5 times x to the half, because we have addition of 2 logs, so 5 times x to the half. But then if I continue, I have a subtraction, which means we're going to have a division there. So divided by x minus 1. Again, that's in the same log. That's okay to write. And then one more step. So we have addition next. Addition. So that means we're going to have a multiplication inside the log. So multiply by x plus 5 cubed. So that's all happening in this log. So that's a product, division, and a product. And all we have to do next is make it look nice. To make it look nice, we're just going to move the term on the x plus 5 cubed, move it into the numerator. So we get log of 5x to the half, x plus 5 to the third power divided by x minus 1. That's all. Any questions? So that's condensing. I have another example. I'm almost done. I have several examples, but we should be able to finish soon. So the next example is we're going to find the following expression without a calculator. Find the following value without a calculator. So the example is 2 log base 9 of 3 minus 4 log base 9 of 3. I hope I didn't write it wrong. I don't like what I wrote. So I'm going to make this addition. Nope, sorry, that's a subtraction. And this is also a subtraction. I fixed the problem. So log base 9 of 1 over 729. So no calculator. And we want to simplify this and get a number out of it. Well, the first thing we can do is, so there's a few things we can do. We can either condense the 3 logs into one step by step, like what we did before, or we can take a quick shortcut. So here we have the first 2 terms. We have 2 log base 9 of 3 minus 4 log base 9 of 3. So if we think, okay, log base 9 of 3 is a chunk, it's think about it's apples, right? We get 2 apples minus 4 apples. We get negative 2 apples. So that's a quick way to combine those 2 logs. So we get negative 2 log base 9 of 3. And we didn't do anything to the last log, so let's leave it minus log base 9 of 1 over 729. So that's the first part. The second step we can do is we can actually combine those into one log base 9. Now inside the log are a little bit different, so we cannot really take the shortcut like we did in the previous step, but we could condense them like we did before, right? We're going to bring a couple of things we have to be careful. So here I have a negative 2. So I'm going to bring the negative 2 together inside the log. And the negative between the logs, you can move it into the second log, make it positive, but again, we can just leave it. So that becomes log base 9 of 3 to the negative 2. That's in the log, minus log base 9 of 1 over 729. You can rewrite that as 729 to the negative 1, or you can just leave it. And now we have log base 9 for both terms, and then we have a subtraction, so that becomes a division in the log. So I get log base 9 of, so you get 3 to the negative 2. You can rewrite that as 1 over 9, or we can just leave it here for now, divided by 1 over 7 29. It doesn't look nice, but hopefully we can simplify. So that becomes log base 9 of, so 3 to the negative 2, I'm going to write as 1 over 9 divided by 1 over 729. So that becomes multiplication of the reciprocal inside the log. So that's a log of 9, 1/9 times 729 over 1. That's not too bad. Perhaps we can simplify. I know that 3 definitely goes into 9 and the 729. So that's a 2, 4, 3. And it looks like a 3 goes into 243 as well. So that's a 1, 8, 1. So what I end up with at this point is log base 9 of 81. The multiplication and the division make it a lot simpler. Okay, so what is this value, log base 9 of 81? Well, I'm going to just call this x. Suppose I don't know what it is, so that's x. And then I have put into the exponential form, I get 9 raised to the x equals 81. Well, 9 to what power give me 81? 9 squared, so x equals 2. Any questions? So that's just, again, use the trick to condense logs into one. I mean, obviously you probably think, okay, can I just find out log base 9 of 3 is and to find log base 9 of 1 over 721? That's perfectly fine, and put in then do all the algebra. But if we condense all the logs, it might make it a little bit easier. It might save some work. Who knows? Maybe it takes about the same amount of time. Okay. The next example I have is, well, again, let me know if you have any questions. Okay. The next example I have is, suppose log base 5 of 6 equals A. I'm going to use capital A. And the log base 5 of 11 is equal to capital B. So A and B are some numbers. I'm just going to use them to represent log base 5 of 6 and a log base 5 of 11. So we're going to find an expression for log base 6 of 55 in terms of A and B. Okay, first of all, if we have a calculator, we don't even have to do this, right? Just put in there. But suppose we don't have a calculator, that's what's given. So what we have to do here is we have to look at log base 6 of 55 and then try to think about it in terms of log base 5 if possible. In the log, maybe we want to have 6 and 11 if that's possible. Well, that's not possible, right? We don't have 66, we only have 55. So the first thing we're going to do is we're going to rewrite log the 55 as a product. So that becomes the log base 6 of 55 is equal to log base 6 of 5 times 11. And now I can separate this into 2 logs. So that becomes log base 6 of 5 plus log base 6 of 11. Okay, that's not very good because I want log base 5, not log base 6, right? If I have log base 5 of 11, I know that's C, but I don't have it. I have log base 6 of 11. Now, this is where we can use the change of base formula. So I'm going to rewrite both logs using log base 5. So I get log base 5 of 5 divided by log base 5 of 6. So recall the change of base formula. log base b of x is equal to log base a, the new base a of x divided by log base a of b. Doesn't matter what a is. In this case, I choose a to be the base 5. Same thing with the second log. I don't like log base 6. I'm going to change it to log base 5. So that's the log base 5 of 11 divided by log base 5 of 6. This is good because we know what log base 5 of 6 is, and we know log base 5 of 11. We also know log base 5 of 5, right, which is 1. So now we can rewrite each term. The numerator of the first fraction becomes 1. Denominator becomes base 5 of 6, that's a, plus the numerator of the second one, log base 5 of 11 is b, and the denominator is a. So we just end up with 1 over a plus b over a, which is 1 plus b over a. Any questions? So we kind of just have to look at what's given and try to think about, okay, how can we rewrite this in terms of products or quotients or maybe exponents? All right, I have one last example. Let me go through it, then we're going to finish the lesson. So the last example I have says, it's taken from the book. So recall in chemistry, pH is given by, so pH is equal to negative log of the concentration of hydrogen ions. So that's the concentration. You can use C. So suppose we say, okay, the concentration of hydrogen ions is C. That same formula becomes P of pH equals negative log of C. And the question is, if the concentration doubles, does pH also double? Or does it become half? How does the pH change? That's a question. Well, let's take a look. So suppose when the concentration is C, so suppose when the concentration is C, we're going to, let's say the pH is equal to P. So that's the pH when the concentration is C. Now we want to know, okay, if the concentration becomes 2C, how does the pH change? So pH formula is negative log of concentration, but now we change the concentration to be twice of the concentration, 2C. What is the new pH in terms of the old one? Well, let's see. So now we have a product inside the log. So 2 times C in the log, so we can rewrite it using the property. So that becomes negative log of 2 plus log of C. And then we can distribute the negative, becomes minus log of 2 minus log of C. Well, if we look at this part, negative log of C, that's just the pH when the concentration equals C, right? So pH equals negative log of C. If that starting pH is P, so this is the starting pH. So that becomes negative log of 2 minus P. Sorry, not minus P, plus P. Because pH equals negative log of concentration equals P for starting concentration. So negative log of C becomes the P. And if we rewrite this, that just becomes P minus log of 2. And if we know what log of 2 is, then we can figure out how much does the pH change. It turns out that log of 2, if we're using the calculator, that's about 0.3. So that becomes P minus 0.3. That's a new pH. So in this example, when the concentration doubles, the pH doesn't even drop by 1, it only dropped by 0.3. So it's a very small change in pH when the concentration increased to twice that amount. Any questions? All right, I think this is a good point to stop. So for homework, I only put problems from 4.2 to 4.4, and that's also what the quiz is going to cover. So let me just quickly remind you that the quiz on Monday covers 4.2 to 4.4. And what I talk about in the second half of the class today is actually 4.5. That's not going to be on it. All right, any questions or comments before I let you go? All right, then. I'll see you Monday. Let me know if you have any questions. Take care, everyone. Bye-bye.
Thank you. Thank
All
you.
right, thank you. Thank you. Bye-bye.
Thanks.
All right, take care, Brian.
You too.
Yeah, bye.